Hello everyone, welcome to my channel. In the last hands-on tutorial, I have shown you how to compile Quantum Espresso in the most simple way. And in the last slides tutorial, I also showed you some aspects of the compilation of Quantum Espresso. If you haven't watched the slides tutorial, I linked the video here, and I strongly suggest that you watch it if you don't have any previous understanding of the compilation process of Quantum Espresso. In today's tutorial, I will continue the compilation last time, and I will show you how to tune the parameters and where to tune the parameters of the compilation. You just go into the folder, and you see this make.inc. This is a very important file which contains the parameters of the compilations. So it specifies the math library, the compiler, the parallel computing library, and everything. So if we open it, maybe we should first do a small recap. Okay, I will make it smaller. Okay. So for the compilation of Quantum Espresso, you need basically three things. One is the compiler, and you need a C compiler and a Fortran compiler. And the second thing is a math library, and you need something called LAPACK or BLAS. So those two are basically the library for linear algebra, or specifically speaking, it is the diagonalization of matrices. And the second one is FFT, so Fourier transform. And the third thing that is needed is the parallel computing library. If you are compiling Quantum Espresso in a parallel version, parallel computing library, and the most widely used protocol is called MPI. Yes, and then the make. I can make this even smaller. So the make.inc file contains all of the informations about the choice of everything. So okay, this is better. It appears to be a very long file, but most of the lines are not even compiled, because you see that the line starting with a hashtag is just a comment. There is no use. It's just that more convenient for you to know what actual code does. So if you scroll down, the first important thing here are those four lines. They specify the compilers. You see that this MPI F90, that is the parallel computing version of Fortran. No, parallel computing version of Fortran. And you see that here it is Fortran, and Fortran does not support any parallel computation. So from here we know that the code generated is a serial version. And the second thing is the F90, that is for the Fortran compiler, and in our case it is also Fortran. And this CC stands for the C compiler, and in our case it is GCC. And this F77, this is also the Fortran compiler. It's just that it is the older version of Fortran language, and here we also use the same Fortran compiler here. And right here you see some parameters for GPU compilation, and I will not go into details of that, because now we will stay with CPU computation, and maybe in the future I will cover the GPU part. And this CPP is the preprocessor for C language. So basically, some part of Quantum Espresso is written in a mixed way of C language and Fortran language. And to compile that file, you have to first compile the C language part and then compile the Fortran language part. So this is the preprocessor of the C language part. This is usually kept as default. Don't have to change it. And what you see here are the flags that are passed to the compiler. And they usually have some subtle influence on the behavior of the compiler. For example, here is -03. -03 is means that it offers a level 3 optimization, which is the highest level of optimization, so that the code will run the fastest. But if you see here, it is -00. It means that there is no optimization. However, you shouldn't change the -00 here, because here it is specifically for Fortran 77, which is a very old standard of Fortran language, and it doesn't support higher level optimization. And if we scroll down here, we will start to see the parameters for the math library. You'll see first here there's a LPAC libs. I'll copy it here. And there's also a blast libs here. Yeah. And what we will see here is that it says that LPAC libs precedes blast libs in loading order, so it will use LPAC libs first. And you see that here the LPAC libs is internal, which means that it doesn't find any external math library, and it uses the one that comes with along with the Quantum Espresso source code. So I will also write internal here. And the next thing is the FFT libs. It is blank here because the internal copy of the FFTW is compiled. So I will also write down that it uses the internal version of the Fourier transform library. The last thing is the MPI library. That is basically the parallel computing library. It's blank here because it doesn't find anything in the environment. So it seems that we have Quantum Espresso compilation with using GNU compiler with internal libraries and without any parallel computation capability. Actually, we can check by going to the same folder as last time for benchmarking, and say make run tests pw serial. So this will run the test of the subprogram pw, which we compiled last time, in a serial way. And it starts running, and you see that the first example is passed, the second example passed. I will stop it. So it seems that the serial version runs correctly. And then we can try the parallel version, and you see that everything failed. Yeah? So indeed, the compilation that we did last time is just a serial version. And if you remember in the slides tutorial about the compilation of Quantum Espresso, I said that GNU compiler is not the best choice. The internal library is also not the best choice, and serial computation is also not a good choice. So in the next video, in the next hands-on video, I will show you how to improve the performance by including a parallel computing library. So I will keep the compiler and math library the same. We just include the capability of parallel computing. So thank you for watching today's tutorial. I hate to say it, but if you find this tutorial very useful, I would greatly appreciate your help by clicking like or subscribe. So, thanks for watching, and I hope to see you next time.